Good now.
All right. So the problem statement is that if a motor were to experience an extra load or resistance against it, without a feedback system, there wouldn't be anything to account for it, thus causing the motor to slow down. So with a control system, it will sense the load against the motor, counteract for that, and then apply more voltage accordingly and speed up the motor to catch up to the desired speed that it needs to be at.
This is a Spartan Superway small scale vehicle. Here are the motors that we're using. They have a 75:1 gearbox ratio. Here's the potentiometer we use to control the speed or to change the speed manually. This is the custom board the team has made last semester and that we're using now with two motor drivers on it. The device is powered by an Arduino, and this is the 7.2 volt battery that we're using.
A typical DC motor diagram will look like this. We have internal resistance, internal inductance, and the back EMF voltage. We also shows the gear ratios and the gearboxes, and also the load shaft that's going to be applied to the load. Knowing this physical diagram, we can find the transfer function. The general transfer function form can be seen at top, where K with the omega speed, omega is the speed, and the V is the input voltage, which is equal to K over tau S plus 1. Tau is called the time constant. And knowing the Kirchhoff voltage law, we came up with the equation for the relationship between the current and the inside the motor versus the input voltage. And we also know the back EMF relationship with respect to the speed of the motor. And knowing the efficiencies, we can also find the output shaft velocity, angular velocity with respect to the input motor velocity. And then the kg and kgl are the motor ratios.
For our demonstration, we placed the vehicle on a straight piece of track. We ran 3 tests, one with the track leveled, another with the track at an incline, and another with the track at an incline without the PID controller. Using the data we got from the Arduino, we plotted each run on the same graph. Here's the velocity over time of all 3 runs. The length of the run does not matter since we are only looking for the vehicle velocity. The vehicle also started and ended at different places on the track. As we can see from the data, the level run had the highest average speed. The incline run was close, however we could not put enough power into the motor to completely compensate for the extra load. The incline run without PID control had an even slower average speed.